Hey guys, GWS here. Here to go through the training of my artificial intelligence.
It's me,
Um,
Mario.
and just first of all, a general overview of what this program is. This is the Q Learning Corruptor. What this does is it will take any file. I've designed this for ROMs and emulators, but this can work on any file. Um, it'll take bytes denoted by the number of corruptions right here. So right here I got 76 bytes being corrupted from the file. What you do, you should go in, you load a file like Mario 64 for example, or hell you can even load, I don't know, anything. I got games here, like you can load it on any game. But yeah, we're right now using on Super Mario 64, and what it'll do is it will alter those bytes according to a set of weights called Q tables. Um, and these Q tables are based on what's called Q reinforcement learning. Q reinforcement learning, if you're not, is a type of machine learning where the learning is based on not on models but on reinforcement. So for example, you've probably heard of machine learning like on Facebook or like self-driving cars, stuff like that. Those use something called model dependent learning. So basically what those are just huge equations that tell an AI like how to, for example, drive a car, right? And how to read the visual input if in a case of a self-driving car, or it could read any number of things. We call those things features, right? Just stuff that it reads. Okay, and then there's the fun one, and this is where AI is kind of going, is you have the non-modeled learning, right? Where instead of based on equations, it's based on reinforcement. So, for example, um, like we load a byte into our corruptor, right? There are 76 of them, but you can even load just one. Um, and what it will do is it will try and come up with bytes to corrupt in the file that will produce a specific desired behavior. So, for example, in our Mario
Mario.
64 example here, we want the game to be able to go into the game without crashing, right? That's a very simple, straightforward way that converts easily to, what an AI can know what to look for. So, for example, let me just go through one as an example, right? So, what we do, this is just one training example. We do hundreds of these, but
Hello.
you push start here, you push
Okie
start.
dokie.
If it gets into here, then we give it a positive reward. So we go to our corrupt button, we hit the 1 key. The 1 key means it's done its job, right? And as you're going to see, this average goes up a little bit. It was 69.0, now it's 69.3. That means that it has done that successfully that percentage of the time. And what it'll do is it'll go into these Q tables. It'll look for the bytes that it altered. And whichever one of these tables shares, that it will, whichever one of these tables the corruption was based on, it will give a positive reinforcement. So let's go into the Q table for an example. Now, don't worry about what these numbers are. That's less important. It's more important to know what the AI does to the numbers, right? So let's just say you get this number right here. This number is one of the features that the bytes have. So what happens is, like, because we gave it a positive reward, um, this number will go down closer to 0. But if we give it a negative reward, um, So let's see if we can find a negative example here to give. It may take a few tries, but we'll go through a few.
Hello. Okie dokie.
Okay, so that's another positive one. This table's very refined
It's
for what
me,
we're trying to do.
Mario.
So it may take us a few
Hello.
times.
Okie dokie.
So this is a positive reward because again we load it into the game, and all we care about is that we see Peach, we see the sky. That means
It's me, Mario.
it's completed all of its loading routines. So we're going to keep hitting 1
Okie
here until
dokie.
we get a fail state. And okay, here's a fail state right here. It crashed at the beginning, so like a naughty little program this thing is, we're going to give it a negative reward. And as you can see, this average will go down. Like, that average will go down, and these values will move closer to 1 by an amount that's called the learning rate. So you can set your learning rate higher, you can set your learning rate low. I'm not going to go into the science or the math of all of it. I just kind of want to show what this involves, and more importantly, how remarkable this AI is. Like, this AI scales immensely, and we're going to show what that's like, right? So what happens is, and this is my training regimen. So we go through this. We'll do this about 100 times. I usually won't do this all at once, because the great thing is like to get from the title screen to where you give the reward, it's less than 5 seconds. So, you know, you take breaks in the middle. You know, you go do something else, come back to it. You know, this is very trainable, and it also trains very quickly. So we do 100 of those, right? We've done 105 because we did these examples. But this is your total here. And don't worry about confidence and accuracy. These are these just try to guess how well the program itself is predicting a positive or a negative outcome. So these values will be removed probably in the near future. I may, if I keep them around, I'll probably change how they work. But I want to add an analytics suite to this, which that'll be like a someday to a procrastinator kind of thing. But anyhow, what you do is you go here, right? And so we had 0.7. So what you do, you go here, you look at your number of corruptions, right? Right now we're on Tiger Algebra because this is the easiest way to do it. But basically it involves taking the root of the number of corruptions that you had. So what we do is you take x to the 76 equals 0.7, because that's 0.7, because that's our total accuracy, right? So we tell it to solve, and then it takes the 76th root down here of 0.7, and this gives us a per byte success rate of 99.532%, which is actually really amazing. It's fast approaching what I thought was going to be the max, because I was thinking 99.8%. You know, and this was an actual 100 things I did in training too. This isn't even a simulation. I just wanted to show you in real time before I did another. So what you do is you go in here to a graphing calculator, right? You enter that number. So you go 0.99532, and getting that exactly is important. Let's close that one. We don't need 2 of those. 532. Okay, and then what you do is you look for the x-intercept. Now I do minus 0.6. This number is important because, like, it's pretty much your desired success rate. So 0.6 means I desire a number of bytes that will get me a 60% success rate, right? And you can even do this at 0.5, and I like to do it at 0.5 because that's generally my metric for how well the AI is performing, right? And then this will get us our new number. So it's either going to be 108 or 109 that we do. We'll probably do 108 to be on the safe side. So that'll be the next number we put in here for the number of corruptions. But if we want to be adventurous and look at 0.5, and if we ever wanted to do 0.5, which you got to be careful because, see, we're talking about like fractions of a percent. Okay, now if you want to do 0.5, you'd end up with putting 147 bytes here. Now, whatever you put here, it's important to recognize something, that right now we're dealing with an extremely high success rate. So right now we have this set at 25 right here. Basically what this does is it will take 25 random bytes, run it through a fitness check to see how it rates on the Q tables that I showed earlier, and then it will select the best one out of those based on the selection type here. So we got 3 selection types. We have PE, which is a pessimistic. Pessimistic means of all the Q tables for a particular value, it will select the one with the lowest fitness or the highest error rate. Okay, and then we got the opposite, which is optimistic, which it will select the lowest. And then we have this, the average, which just takes the average of all the Q tables, and then that's what it will issue the value based upon, right? We're going to leave it on average, but it's not going to matter here because, see, this 25 here, it selects from 25 random bytes. It will select that, the best out of those, and it'll do that 76 times. So we'll end up with 76 bytes corrupted that are the best of 25 selected. And the amazing thing of why that scales is if you look at the per byte error rate, or the per byte success rate. No, it'd be the error rate, excuse me, of 10%. Right, that's the number of times this will fail to reach the Princess Peach letter in Mario 64. So you'll have 10% of the time that will typically fail. Right? Under normal circumstances, if you were to do this right here, try to do 76 out of that, there's my tier list, but let's do 76. You go 0.9 to the 76th power. Okay, and then what is that? Well, we can solve for that. 0.9 to the 76th power is 0.00033 or 0.03%. That means 3 out of 10,000 times you will ever get one positive result. Right? Okay, but what this does, why you use 25 values here is it counterbalances the error rate. So, for example, you have a 10% error rate, but if you're selecting between 2 bytes, that means you're doing a 10% error rate twice. And the chances that both of those, because we're selecting from the best, we want the byte that's going to succeed. The chance that both 10% probabilities will fail, if you look at probability theory, is 1%. And then if you take 3 bytes randomly with a 10% failure rate, you end up with 0.1%. So let's kind of walk you through, because this is probably sounding like mumbo jumbo here. So what we're going to do, Okay, so we got 0.1. So what you do is you square that. That just means we're taking two different corruptions. Okay? And that's 1%. 0.01. It's just another thing for 1%. So if you cube it, which means you take three values, then you just move it over, right? So 0.1%. And then 0.01% fail rate. And so on. So it's like as you're adding bytes, you're decreasing that fail rate. So for example, if we take, we take 0.1 of the 76 again, or 0.9 of the 76, because this is we're dealing with the success rate here, right? So, this is our 0.03%, right? 0.00033 probability. But, if we take our 99% chance of success, and we do that, this is just 2 bytes, by the way. This is 2 bytes in an ideal scenario, right? If we're corrupting 2 bytes, and we have a 1% failure rate, this chance of success goes from 0.03 to 46.588%. So almost a coin flip, just from 1 byte, right? And so what happens is, like, every time you add a number to this, it adds another 0. So for 25, you add literally 25 nines. So this is 12 nines right here, and it's going to give an error because it's way too big, right? Okay, yeah, it's way too big. It's not going to calculate it for us. But the point I'm trying to make is, like, you go 9.3 nines, you get 92.6%, right? And that's ideal, and so let's add another 9 here, just for fun. Then we go from 99.243. Now the kicker is, you're never going to get to that kind of thing, because that assumes that it's always going to pick the best byte. And this is where AI comes in, because you can write all kinds of human-made rules about, like, how do you figure out which random byte is going to crash the game, or which location within a file is going to cause the file to behave in a way you don't want. And this is where the AI really learns. But the thing is like, when you're talking about taking something to the 25th power, you don't have to know a lot about the byte you're dealing with. And that's where the scalability comes into play. In fact, you really need to know very little about the byte in itself. So, like, for example, we're taking that to the 25th power. Like, an ideal would be like 25 nines here. But what we're really asking, is just like 0.999% or 0.998. Right? That's the goal. 99.8% accuracy is where I initially thought this could go. No, it may be able to go a little higher. It may be able to go 99.91% for all I know. I don't know what the limit's going to be. But there's going to be a limit, because, number one, like, as you start increasing your number of corruptions, you get into lots of dependencies where one byte can cause another byte to crash that otherwise wouldn't. And you start getting into very complicated probabilities, because when you look at how this is programmed in C, Super Mario 64, where something that crashes the program, a lot of things are just going to be beyond what you can get to with Q tables that can learn in a reasonable amount of time, even given an extremely efficient and fast algorithm such as what's here, right? Because, you know, the amount of information you have to feed to the tables becomes exponential too. Like this is, you know, this whole thing is just an exponential Jenga tower, right? Okay, so now let's kind of go into what does this mean? Like, what does all this numeric mumbo jumbo translate to? Right? And I want to show you, like, how remarkable this is. And I'm going to show you how remarkable this is by, we're going to take off the learning. We're going to turn off the learning, meaning that none of the tables are going to learn because I don't want to screw up the learning that I've already done. So what I'm going to do is I'm going to set this to 1. Setting this to 1 means it's not going to compete with anything. It's just going to corrupt 76 purely random bytes, right? Now, we went through the numbers. The success rate is going to be about 3 in 10,000. Okay? And I want to show you what that looks like. And I want to show you, you know, we'll probably go through 20 or 30, but you could do this hundreds of times, and you'd be lucky to get one positive result. So we're gonna go through this, and I'm gonna prove my point here. So, you know, we're gonna turn on our thing, and we're gonna go through this. Okay, fail, 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 and fail. Now we did this 25 times. Like I said, you could do this hundreds of times and you'll never get a positive result because it is so hard. And the thing too, one other thing to understand is it's worse than the math even suggests, because there are so many things where you screw up one thing in the assembly and you screw up the entire file. So again, like I was explaining before, the byte interdependencies really come into play, and they come into play fast if you don't have an AI optimizing it. So let's turn back on our AI, and let's put this at 25 like we had it, and then we'll show you the AI in action. So we had 0% out of 25 attempts. Like I said, this could have been 125 attempts for all we knew. So we're going to reset, and we're going to run this. So that's a fail. That's a fail. That's a fail. That's going to embarrass me. It's okay, here we go.
It's me, Mario.
So we got one on the 5th attempt, and that's really...
Hello. Okie
That was an
dokie.
interesting thing. Mario red face. Hang on, I gotta look at that. Okay. Well, we won't reward it yet, but I want to see this a second. So bear with me as you get some free content. See, this is... And these are the kinds of things that you get with
It's me,
corruptions, too. You just get
Mario.
random shit.
Hello.
Like, see? You see how the lighting changed right there? That's pretty neat. We're actually going to save this one. That is interesting as hell. Like, you got, like, a pink light instead of that. And it's like I said, like, And AI, that's what it's going to find for you. So pink like Mario head. Now let's continue. So we got that closed, so we could still give it a reward because we still have our thing loaded. So we'll reward it. Right now we're at 20%. Right now it's not doing particularly well, but you know, this will kind of average out too.
Hello. Okie dokie.
Because we were at about 70%. See, like, even though it's doing
Mario.
pretty badly right now, if you look at,
Hello. Okie dokie.
like, O of 25, like, this is a remarkable improvement. As you can see, the average is going to start averaging out here. You know, we'll take it to 25, and we'll just kind of see where it's at, right? You know, and it's running into a lot of hard luck stuff. You know, that's going to happen. You know, you're going to get bad streaks. You know, that's why it's important to have a resilient AI, too. Because what can happen is you get those bad streaks, you get a lot of false negatives, and it could topple your AI down. That's why you gotta be really careful with how you train these AIs. Like when you get above 99% accuracy, like even a drop of like 0.1% will be missed. Like it'll mean, you know, this working 70% of the time to probably less than 10%. Right? It's nothing you really want to fool with. So, we had our bad streak of luck. We're not training anything, so nothing's being reinforced.
It's me, Mario. Hello. Okie dokie.
Yeah, at least we better not be training anything, but no, I'm pretty sure
Mario.
I hard set that.
Hello. Okie dokie.
Okay, so now we're at 50. You know, we had a rough stretch, but now we're getting a good streak going. But like I said, compare this to the 1 in 25. And, you know, like I said, if I would have run this, you know, I don't want to waste your time, or mine, rather, because, you know, it takes a little bit of time to run these training sessions. And so, you know, I could have run that 100 times and I wouldn't have gotten a single positive. So, for us to be at 50% here, that is remarkable. You know, so we did the same amount of time. Again, compare 52% to 0%. That's the difference with a good AI. That is a very, very big difference. And again, unlike many other things you'll see, this AI scales tremendously fast if you can keep it stable. You know, you don't want to be greedy with your learning rate, and that's important. Like, you want to have, like, to start, you may want to set it very high, even at 1, just so it can kind of learn how to navigate around the file space and make predictions based on what rewards you've given it. You may want to have like an initial high, but ultimately, you know, you're going to want to have your learning rate very low, where it can make slow incremental steps, and it can be resilient against bad streaks or dependencies or just things completely out of the control of the AI, where it could predict a positive outcome, but it won't come true. But this isn't going to be the main video about how to use this. We're going to go through at a later date. Once I get an official presentation, you know, I may even fluff this out a bit. There's an analytics suite I have to add. There's stuff I have to remove. Obviously, this is very ugly aesthetically. I may have to get some art direction for it. But this is just a basic introduction into my process of training the AI, because certain people in Discord were a little bit curious, so I just figure, let's make a video about me going through the process. And as you can see, you saw me go through both calculating how to set the number of bytes I'm corrupting, and how to scale everything up, a little bit of the internal math, not quite into the internal processes of my program, because, I would like, I'd like to make something of this program, because it's a work of love for me, but it is hard work. It does take a lot of hours. So there is all that. But anyhow, I'm glad I got to show you guys a little bit of something, and thank you for listening, and God bless everybody. Love you.